Okay, let's wait for 1 more minute for the students to join. Let me put in a new slide for discussion. Slide, put a blank slide. Presentation and let me pick the pen. All right, so let's continue because we have only 50 more minutes. So we now have a lot of these in the solution, right? We now have a lot of silver neutral atoms in the solution, and what will happen now? Let me just draw them as small dots like this. Okay. Ah, all right. So all these are the silver atoms now moving around in random motion. Okay. They are moving around like this. You never know the direction. You cannot predict the direction. They are in constant random motion. Okay. So now mm, they will now start colliding. They will start hitting, and what will happen is, say, suppose three of them now come together. There will be many such three coming together all over the liquid. All right, the solvent, you will have many such atoms coming together. Okay, you cannot be so consistent. You cannot say that all will be three. One may be four also. Okay, something like this. So you cannot. We are not consistent. We have a size range. Okay, and we have many of these forming. So this is the starting of the formation of the nanoparticles, and we call this process as the nucleation process. All right, the nucleation process. Now all these nuclei are instantly formed. Okay, now instead of these atoms like here, instead of the atoms moving around now in the liquid, we have nuclei moving around now. All right, and we are still giving the excitation. That means the heat is still there. That means these nuclei are also in an agitated state. What will happen now? These nuclei start to come together. That means suppose there were three. Now three of these nuclei came together and they became now suppose 9 of those put in together. Okay, so you will have slightly bigger particles now because the nuclei have started coming together. Three nuclei suppose came together and became slightly bigger. All right, so this is the next stage. Now this process of conversion from the nuclei, because these are called nuclei individually, each one is a nucleus. Okay, and in full form plural we are saying nuclei. So this from nuclei to the next phase, okay, slightly bigger particles. This process of happening here, also the heat is still there. Okay, we are not removing the heat. The heat will constantly be there. Then this process is called, I already mentioned once, Oswald ripening. Right. Okay, Oswald ripening. Fine. So this will keep on continuing as long as you are keeping the excitation source coming in. That means starting with maybe 1 or 2 nanometer nuclei. This will go on increasing, maybe 5 nanometer. Maybe next we are going to 7 nanometer. Okay. So the process will go on that way. 7 nanometer. Maybe the next one will be 15 nanometers. Okay. And suppose you want the particles, that means your requirement is a particle of size around 15 nanometers. All right. Now, the moment it becomes 15 nanometer or around 15 nanometer, what we will have to do? We will have to cut out the excitation source. All right. We have to cut out the excitation source and we have to reverse. I won't say reverse, but we have to create a situation that immediately no further agglomeration or no further austral ripening happens. Now, the moment you cut out the heat, what will happen? The water is suppose at 90 degrees or 95 degrees centigrade. If you cut out the source, even then it will be at 90-95 for at least a few more minutes. Gradually, the temperature will come. And in that process, from 15 nanometers, you might land up with 20 nanometers, right? And that's why simply cutting out the heat will not do. We will have to go for a process which is called quenching. Quen, uh, Q-U-E-N, let me cut this out. Write it here. Quenching. Okay, quenching. Okay, I'll give you a note later, so don't worry. But this is the spelling Quenching. Quench means to stop, abruptly stop. Okay, so how do we do that? How do we quench it? We freeze it. Okay, we freeze it. Ah, let me just put in a. Let me just put in. What we do? We let me write the term again. What we do? We quench it. All right, the process is called quenching. Fine. So we quench the reaction. That means we take it out from the hot condition and put it in the fridge or in a liquid or in water which is at a you can say ice water, ice cold water. Then what will happen? Instantly, the movement or the amount of energy in the nanoparticles will go down. Right? The movement will go down and the movement will not be strong enough to continue the austral ripening. Right? Now, when I'm explaining to you all these, it appears very simple, okay, but it is not as simple as you think. See, I told you before that the atoms in the ionic form, when they're 3+ charges on them, they are not coming together, right? Because they're repelling each other. And at the atomic level, 3 units of positive charge is quite a big charge, all right? So 3 units of positive, so it's like big positive charges coming together, and that's why they will repel. Now, after we removed the charges and converted, that means through the reducing process, we added electrons, we removed the charges and allowed the atoms to come together. But as they are slowly becoming bigger and bigger, what happens is that there are charges that come and sit on the surface, right? They are not charges which are subatomic in nature. That means they are not charges because we are removing electrons, but because of the presence of other charges in the solution. Because if you remember, when we first dissociated, we had sodium, silver plus 3, and NO3 minus is also there, right? So that will also might break, and we have a lot of positive and negative charges present in the solution. Okay, there are charges there. The charges cannot vanish, because otherwise overall it's neutral. So all those charges start sitting on the surface of the nanoparticle. As the nanoparticle becomes bigger and bigger, more and more charges come and sit on it. All right, which is called the surface charge. I'll come to that later. But you think about it now. You don't think that the particles are, coming in through Ostwald ripening, becoming bigger and bigger. It's very easy because they have no charges. No, they actually started getting charges as they become bigger and bigger. And gradually, that's why the repulsive forces start coming in again. All right. So you will see a drop in the growth rate with time, right? That means how fast the nuclei formed, how fast the first nanoparticles form. It was much faster than gradually as the nanoparticle becomes bigger and bigger because of these charges sitting on the surface that will start repelling each other. Okay, and that's why the moment we remove the excitation sources, we freeze the, we cannot make it ice, but we put the solution in a ice bath, then automatically the energy that these nanoparticles, they're already becoming bigger. Okay, they are not atoms anymore, they are a few thousand atoms together, right? So they're already heavy, and that's why they will lose that amount of energy needed to overcome that repulsive force of the charges sitting on it to go for further agglomeration and further increase in size. And that's why after quenching we get what we call very stable particles that do not become bigger. That means the Ostwald ripening will totally stop. And this, suppose I'm giving the same example of silver at the moment. So these silver nanoparticles that we make, maybe 15 nanometers, maybe 20 nanometers as per our requirement, all right? And then we can store them. And metallic nanoparticles are very stable in the sense that you don't really need to keep them in a refrigerator also. You can just keep it outside. Of course, you have to cover it, otherwise there will be contamination. But you can keep it outside on the shelf, okay, because the room temperature is not enough to further initiate the Ostwald ripening, right? And that's why at room temperature, you can nicely keep the nanoparticles for months together, okay? They will remain almost the same. But even then, like silver, it has certain effect of light on it also. So you keep it in very bright condition, you might gradually see a change in color. That means the particles might become bigger or even smaller sometimes, okay? Because sometimes they break up. Now you will observe a change in color because I already told you the color changes with the size. Especially for metal nanoparticles, this becomes very, very clear. You can nicely see the change in color. Semiconductor particles are not very colorful. Okay, some are there, of course. I'll come to that, but this size variation, color variation together is prominently seen in metallic nanoparticles and some other, sulfide quantum dots. Okay, those I'll show you later. But at the moment, let's talk about metallic particles. So even though they're very stable, you can also see some with time. You will see some changes coming in. Right. So now, what is happening here now? You see, you did not add anything else. You simply added the source of silver and you added a reducing agent, right? To put in the electrons, nothing more. It is other things are simply heat, all right? You're putting in heat as an excitation source and then you're quenching it, putting in a water, an ice cold water bath, and done. Your particles are ready. And after that, I'm saying the particles do not agglomerate, right? So why is that happening? I mean, I already said no, there are some charges sitting on it, and these charges do not allow them to come together. They repel each other because they are like charges. So this type of condition where the particles are very stable, I mean, they are not changing their shape, they are not changing their size, okay, they are not agglomerating, coming together, then it is called a very, very stable condition. All right. stable condition. Now I will introduce a term here. Let me just write it here itself. The term is colloid. Now, what we just made is actually a colloid. So what is colloid? Colloid is something that is a solution. I'll rather not use the correct word will not be solution. I'll say a liquid which has a lot of particles, some form of particles suspended in it, and they are stable. They do not agglomerate. That is a example of a colloid. Okay. Now see the difference. Initially, we had what we did. We put in silver nitrate and dissolved it, right? And I said the silver nitrate got dissociated, silver ions came out. Now that condition, now we are talking about atoms, not particles, right? So when there are these atoms in a solution, it in liquid, that means the solvent, it is a solution, right? So when we have all these atoms moving around, it is a solution. And if we have particles, which are not single atoms, there are many atoms together, and they may be in various shapes, sizes, all those, but they are stable. I mean, they do not agglomerate, they do not fall down. They do not fall down. You understand? That means there's no gravitational effect on these particles, and they're moving around in the liquid. Then that is what is called as a colloid. Okay. Now the particles will remain there suspended nicely in the colloid as long as there is a stability. That means what we call as the colloid is stable. Right? If there is some instability coming in, then all those particles we are seeing suspended, moving around, they will start coming together and they will settle down at the bottom of the container. Okay. All right. Now let me try to explain this even easier. So. Uh, You all know how to make cottage cheese. You know what is cottage cheese? Can somebody tell me what is cottage cheese? Anybody knows? Tell me, what is cottage cheese? Someone? Nobody? Well, we call it, we call it what? We call it paneer. Okay, so paneer is actually cottage cheese, and it's popular all over the world. Do you know how you make it? Have you seen somebody making it? Maybe at home? Very simple. You warm up a milk to a certain temperature, and then what do you do?
In
You
the card, card.
no, yeah, something that has citric acid. Best is lemon. You take some lemon and just put the lemon juice. Instantly, you'll see the milk is slowly breaking up. You understand? That even whitish color, now you'll see gradually some particles forming, and these particles agglomerating and keep on heating, and gradually after some time everything settles down. You get the white paneer, right? So milk is a very good example of a naturally made colloid, right? So there's so many particles in the milk. So the moment we put the citric acid, all right, that means the lemon juice, what will happen? The colloid gets destabilized. So initially in milk, it is a stabilized colloid. So take out as much milk as you want from with a spoon. You'll always see the same. All right. You cannot see any particles. You cannot see anything. It's the same white liquid. Then the moment you added the lime or the lemon, it's separated out. That means the original things that are nicely suspended, they started agglomerating, they started coming together, they started becoming heavier, and they separate out. That means the stable milk colloid came to a form which is a destabilized colloid now, destabilized milk colloid, right? So as long as you can keep a colloid stable, then the particles will always remain suspended. So that is another challenge. We people who are working in nanotechnology, for us, the challenge is how to keep a colloid stable. That's why if you come up with a new way of making nanoparticles, you said, okay, I made some nanoparticles which are of 5 nanometers, they are this shape, that shape, this is the process I have made. People will immediately ask you, how stable is the colloid you have made? Right? How stable? For how long will it remain stable? What is the shelf life of the colloid? So that is very important. It's not only about making. You have to ensure that whatever you have made, that means the particles suspended in a liquid, the colloidal particles, they have to be stable. Now there are various ways of doing that also. I'll come to the stability of colloids later. But right now, what I'm trying to say is that these silver nanoparticles also, if you keep on heating, the particle will become bigger and bigger, like suppose 15 nanometers, 25 nanometers, 30 nanometers, 35 nanometers. It goes on becoming bigger. You are not stopping the reaction, you are not quenching the reaction. So what will happen? Ultimately, they become so big that the effect of gravity comes in. And then slowly they will settle down. And you won't have anything in the liquid. Right? Everything will settle down and you won't have those small nanoparticles. So that is an example of instability. That's an unstable colloid. Okay, and that's what happens with time also. Like I told you, if you keep it for a long time on the shelf, gradually you might see them settling down. That means the silver nanoparticles, suppose I make some silver nanoparticles which is yellowish in color or brownish in color, suppose. So I'm keeping it in the shelf. I see the brown color nicely for months, and then gradually I will see that the color is fading. And then if I observe, I'll see something sitting at the bottom of the beaker or the test tube, wherever you keep it. And you continue that way, after a few days or a few months maybe, you will see that the liquid is transparent, water is transparent, and you will see some yellowish powder at the bottom. That means they've already started agglomerating, they have become bigger, and they are in the macro scale now. They are not in the nano scale anymore. All right, now this process of synthesis of silver nanoparticles or metallic nanoparticles, is it okay for you? Did you understand? Or you have any questions regarding this? You can ask me now if you have. No questions means everything is very clear, right? Okay, good. So the similar process goes for all types of metallic nanoparticles. Okay, the reactants will be different, of course, because like I told you, the formation of these nanostructures or different nanomaterials, if you go for the bottom up process, there is a big impact of the pH, temperature, concentration. All right, so these have a huge role to play, and that's why, based on what type of particles you want, what type of sizes you want, what type of shapes you want, you will have to set these initial conditions, right? So, if I show you those slides again, let me go back to this slide. See here, all these particles, they are made at different pH. Like I change the pH. You can change pH. Like if you want to make it acidic, you would drop in some acid. If you want to make it basic, you would drop in some base, right? So if you want to take the pH from 10 to 12, you simply add some sodium hydroxide or potassium hydroxide, or they automatically will go up. And if you want to make it acidic, say around 6, from 8 to 6 you want to take, you put in some drops of acid, hydrochloric acid maybe, or sulfuric acid. All right. So that's how we do it. So we can create those conditions just before the particles form. All right. And based on those conditions, the particles will be different. Like you see here, they are very, very long rods. And look at this one. This is a flat tablet. Okay, very flat. Same conditions in the sense that all here all the temperatures are same, okay? Because all of these I have cooked at around 90 degrees centigrade. All of these. That means temperature was not variable for me. I had kept temperature fixed. The only thing that was variable to me for all these structures is the time and the pH, right? So pH and time, just by playing around with pH and time, you see so many variations in the shape. Okay, so that's why you need to set these conditions. Now you have a lot of these information available. When I started my work, there was not much of information available because people didn't know. People didn't, they were making, but they didn't know. There was no systematic study. And then it came to me, it dawned to me, you can say, I made a realization that it's something that has to be done. And that's why for this particular material, zinc oxide, as far as the nanomaterials are concerned, nanostructures are concerned, I did a very, very systematic study. You'll find all my papers. I can share some later with you. But even if you Google and go to Wikipedia, you just type in zinc oxide in Wikipedia, if you look at the references, you'll see a lot of my work presented there. Because I think I was one of the first person to have systematically studied the growth, right? Why this is happening. So it took in, of course, almost 2 years I had spent on studying how this happens. So, but then it's so interesting. And that's why I'm saying that this is a lot of unexplored areas here. You don't know, because unless you do this, it's very difficult to predict, like the gold nanoparticles we made, the group I was working in, there are other members also, we made a systematic study on the formation of these gold nanoparticles. So now we are in a condition where we can say that you tell us what you want. You say, I want 22 nanometer size particles. We will give you the recipe for it because we had done those initial studies. Okay, we have done those studies, we have plotted the curves, and we know. We simply plug in the value in the curve, and we know, okay, this is the condition you use, and you'll get these particles. This is the time you need. Okay, these are the concentration of the reactants you need, and you'll get it. So that's why this type of work has to be done. That's why it's not done for every type of nanomaterial, and that's why when we are starting out with a new type of material, we need to do a lot of study ourselves. Okay, because there are no available data sheets that can help you to get the exact thing that you want. Okay, that's why you need to move in a lot of efforts. But this journey is very interesting. Okay, so now I was talking about metallic nanoparticles. The same will be for gold. For gold, we use a salt called chloroauric acid. Okay, let me just so here we were talking, let me just put in another slide. New slide, blank. Okay, let me put in a text box. So we are now talking about gold nanoparticles. Okay, gold is AU, right? Silver is AG, gold is AU. Comes from aurum. Silver comes from argentum, right? So these are Latin words. All right, so gold nanoparticles. It's the same process like silver. Okay, so here what we do is the salt that we start out with for the gold. All right, the salt that we start out with for the gold is chloroauric acid. Okay, this is the name of the salt. Actually the chemical formula is HAuCl. Where is the subscript? HAuCl 4. Okay, so here 4 is a subscript. I forgot what it is. Subscript, is it control minus or alt minus? No. Anyway, this is HAuCl4. 4 is below. It should be there. No, where is it? Should be somewhere here. Okay. So That is the salt we are using. And you see here gold is there, right? This is gold. So, and the typical reducing agent that you want to use, you can go for sodium borohydride like we did for silver. You can use that also. Or there is another one called, it's a very popular one. It's called trisodium citrate. Oh, okay. Now again, this is in subscript. All right, it's called trisodium citrate. So it's very similar process, but we will use chlororic acid, same way, dissolve in water, heat it up, add the trisodium citrate, or there are many. Like I said, trisodium citrate can be one, or sodium borohydride can be another one. Okay, or you can have monosodium glutamate. Okay, so these are some reducing agents for making gold nanoparticles. Fine. So that way we can work on. So the idea with metallic nanoparticles is that we first dissociate. That means from a salt, we remove all the metal we want into the water, and then we use a reducing agent to provide the electrons to make it neutral, and then we continue excitation and allow the Ostwald ripening to happen, and we get our nanoparticles. Okay, very simple, right? So I don't want to move over to semiconductor nanoparticles today because I'll not be able to finish, and so I will pick up the metal semiconductor nanoparticles in the next class. But I would like to have another class this week. Is it possible? Can you guys give me some time from your schedule? See, let me tell you here. I was a visiting faculty after I returned to India and I joined Don Bosco University. I was a visiting faculty for the Asian Institute of Technology, which is my alma mater. I was working, studying there. I worked there, so they wanted me back to go and teach, and that's why I went. I used to often go as a visiting faculty for 1 month or 1.5 months, and I will take classes, many classes, so that I can finish off the courses in just 1 or 1.5 months. And because there's a maximum leave I used to get, and I remember once, I asked for an extra class, okay, from the students, and I said, you give me some extra classes because there's a lot to finish off. And these are undergraduate students like you, huh? So they said, okay, sir, we'll give you 3 hours from 9 to 12. I said, well, wonderful, 3 hours, I'll manage. So 9 o'clock, I was in the lecture hall, nobody around. I was waiting, and after 10, 15 minutes, I just decided to call one of the students. I called the guy and I said, hey, what happened, you guys? You said 9. No, sir, sorry. We forgot to mention. We meant 9 p.m. That means from 9 p.m. to midnight. That was the time they gave me for the class. And it's so exciting, believe me. The problem is in India, we follow a very, very, disciplined type of a lifestyle, which for me is not really, I'm not used to that. I'm more used to the chaotic form of life. So I wouldn't mind if you guys tell me that the only time we can give you is from 11 to midnight. That is also okay with me, as long as it's okay with you. It's okay. So I will need 1 more hour this week. So let me know when you can give me the time. But of course, I also have other meetings to go into. But give me some time if you can, after 5, after 6, because anyway it's lockdown. You guys are at home. If you can give me 1 hour, then we will have, because we needed to continue put in some more time here. So let me know this week itself, okay? So today is Wednesday, Thursday, Friday, Saturday. We have 3 days. Just give me 1 hour slot, preferably in the evening. Then I don't worry have to worry about the meetings, right? Let's see if you guys are okay with that. And if it means one student saying I want to attend, I'll take the class. Fine. So, anything to ask now from today's class? Any doubts? Anything to clarify? Are you guys there?
Yes, sir.
Yes, sir.
Yes,
So,
sir. Yes, sir.
is
Yes.
this clear what I was trying to explain regarding the metallic nanoparticles? How to make them?
Yes, sir.
Yes. Okay, good. Don't worry. I'm not going to ask questions to test your knowledge. I mean, I just want you to be happy that you have understood. Okay. Because otherwise, as we go more and more into the courses, things will become even more difficult for you to understand if you don't clear the small doubts now. Okay. But anyway, you can always put it in the WhatsApp group if you have any doubts. And don't think that me or anybody else will laugh at your questions if you come up with something very stupid. Also, it's absolutely fine as long as it clears some doubts for you. Okay, so just don't hesitate. And so the next class that you give me this week, I will pick up the synthesis of some semiconductor nanoparticles. Okay, so you let me know when you can do that. And so I'll stop now if you don't have any questions. So please put in your attendance now. Okay, and we will meet in the next slot that you guys give me. Okay, so let's stop here now. Thanks, guys. Take care. Okay.
Yes, sir.
My just class touch. You give me another 10 minutes. My class time choreography. My call back choreography. I'll call you. Okay, everyone. Bye.
Excuse me, sir.